we're going to consider an important application of eigenvalues and eigenvectors called differential equations. Now, just to give some sense of what this is, let's start with the usual equation we're used to. This is what's called an algebraic equation. In an algebraic equation, we ask which number would make the left-hand side of this equation equal the right-hand side. So in a simple equation like this, we could factor it and see very easily that the only way the left side would be equal to the right side is if the x was the number -1. Now, a differential equation is more complex. It says which function x of t would make the left-hand side equal the right-hand side. Now, a differential equation involves the mystery function plus its derivatives. There's an entire branch of math that's dedicated to the solution of differential equations. And you can see that it becomes quite challenging to solve this. It isn't as straightforward. Now, you might ask, why would we care about a differential equation? DEs occur in all branches of science, engineering, and math. They are everywhere. And as an example for us, we are going to talk about a series circuit, and we're going to introduce some new components to these circuits. First, we're going to talk about what's called an RL circuit. Now, an RL circuit contains a resistor, and it also contains something called an inductor. So the schematic here for the circuit looks like this. This is our usual resistor. This object here is called the inductor. What we need to do is talk about Kirchhoff's laws. Now, there is no voltage source in this particular circuit. We know that the voltage loss has to be due to the voltage loss across the resistor plus the voltage loss across the inductor. So there's going to be some sort of current flowing here, and we are going to assume that once we turn this switch on, there is some initial current. We know from Ohm's law that the voltage loss across the resistor is just R, the value of the resistance, times this current, I of t. Now, an inductor responds to changes in current. So it will turn out that the voltage loss across an inductor is proportional to the change in current as a function of time. So what this ends up producing is a first-order differential equation. We are looking for this function I of t, and its first derivative appears, and that's the highest derivative. Now, we can prove that the solutions are of the form constant e to the kt. Now, both of these things, c and k, are constants. So what we're going to do is sub this form of I of t into the dE. So if we were to take the derivative of this expression, remember that we can use basic linearity, and then we'll need to use the chain rule. This is going to produce ck e to the kt. And when we sub this into the differential equation, we'll have 0, r times c times e to the kt, L times C times K times E to the KT. So you can see immediately that there's a common factor of C e to the KT. And when I remove that common factor, I'll have the following. This exponential is never 0. So my choices are either C is 0, which is just the trivial solution, which means there is no current flowing in the circuit. So we're going to ignore that. Or the other option is if that factor is equal to 0. This K is negative R over L. So that means there are infinitely many solutions to this particular problem. So it will turn out that we can get a unique solution if we apply our initial conditions. So the initial conditions told us that the initial current was some constant value. So if I were to take this solution and plug it in, I'd have C e to the negative R over L times 0 is equal to I naught. So this tells me immediately that C is I naught. The current through this RL series circuit looks like this. So this is what's called the natural response of an RL circuit, a decaying exponential current as a function of time. It simply decays down to 0. The current is time dependent. And this is very different than what you find in a regular circuit that just has a resistor. Now, there are other components in a circuit that will lead us to a system of first order DEs. Now we're going to talk about something called a series RLC circuit. So we are going to have this component here, this new double line is called a capacitor. We'll have our resistor, and then we'll have our inductor as we had before. Now you can think of the capacitor as a voltage source. It's kind of like a battery that can charge and discharge, whereas the inductor you could think of as a current source. As before, we're going to use Kirchhoff's laws. The voltage source here is the capacitor. You can show, and you will learn this in courses on electronics, the rate of change of the voltage across the capacitor is proportional to 1 over a constant called the capacitance times the current that flows through. From this equation right here, VL is simply VC minus VR, or L times I prime of t is V of t, we're going to call this V of t, minus Ri. In a circuit like this, the voltage across the capacitor changes in time, and the current through the circuit changes in time. So what we have are two unknowns here. So if we were to set up a system of equations, we would have I prime of t is 1 over L times V of t minus R over L times I of t. V prime of t is simply 1 over C times I of t. What we produce here is a system of first order DEs, and there are two unknowns, this V of t and I of t. This is what's called a coupled system because the I equation depends on both V and I, and the V equation depends on both V and I. We're now going to use vectors and matrices. So if we say that the vector x of t is a vector function, and it now holds our two unknown, and if we define x prime of t as the derivative of this vector function, we are going to define that as the derivative of each individual component, I prime of t and V prime of t. Then there's a way for us to rewrite that system that we had above. I prime of t and V prime of t are components in a vector, and the first component we had negative R over L times I of t plus 1 over L times V of t, and we had 1 over C times I of t. We have 0 bunches of V of t. If we introduce our unknown vector again, what this produces is a matrix vector product. And we'll have negative R over L, 1 over C, and 0. And as such, this can be written a lot more compactly as x prime of t. We'll define this matrix as A and our unknown vector x of t. And once again, this is a system of first order DEs. Because of this, we are going to say it's a linear system because, as you can see from this equation above, none of our function or its derivatives appear to anything other than the first power. So naturally, the question is, how do we solve this particular system? And we're going to use the idea that we had from above. For a single first order equation, we needed an exponential form. We are going to try the solution vector x of t is proportional to e to the lambda t. And because this needs to be a vector, we need to turn this into a vector. So we are going to put in some constant vector right here. Now, what's really important here is that this vector is not 0, because if it were 0, we would just get the trivial solution, and then there would be no point in solving it. So this is the solution form that we're going to try. We're going to write this a little more generally. If we have a first order system, we can say that this is some u of t and some v of t. A first order system would look like this. We'd have u prime and v prime equals a, b, c, and d, u and v. And this would turn out to give us u prime and v prime is au plus bv and cu plus dv. And we're going to assume that all of these things in here are constants. So our coupled system ends up looking like this. U prime of t is au of t plus BV of t, and V prime of t is CU of t plus DV of t. So we are going to try a solution vector that looks like this, V e to the lambda t. The derivative of this solution vector would simply be the derivative of this expression above. Because the V is a constant, we can take it out, and what we'll end up getting is lambda V e to the lambda t. So what we're going to do is sub this into our system of first order equations. X prime equals AX. This is going to produce a lambda V e to the lambda t on the left, A times V e to the lambda t on the right. Reorganize this equation. A V e to the lambda t subtract lambda V e to the lambda t is the zero vector. There's a constant factor of e to the lambda t that I can take out, and you should see that this is going to start to look familiar. I'm going to rewrite this term as lambda times the identity matrix acting on V. Now have the following. A minus lambda I times this vector V is 0. Because this can never be 0, what we are left with is our usual eigenvalue eigenvector problem. So here is the point of all of this. If this is the solution form, V e to the lambda t, this is an eigenvalue of the matrix A, and this is an eigenvector of the matrix A. So what we need to do is we need to solve another eigenvalue problem. And so this ends up being a wonderful application of eigenvalues and eigenvectors. As always, in order for this to work, matrix A must be square. It is not possible for us to have an eigenvalue problem unless we have square matrices.